Today we are going to start chapter 21, which is electromagnetic induction. And before we go to the actual electromagnetic induction formula and how to find it, we have to know what magnetic flux is. So do you remember electric flux from Gauss's law? So it is the same equation here. The only difference is instead of the electric field, we have the magnetic field for magnetic flux. So what do we mean by flux? So magnetic flux is the amount of magnetic field lines which will go through some surface. So it is the amount of magnetic field lines which will cut through a surface or go through a surface. If you remember, this theta here tells you that the angle that it cuts the surface matters. For example, if your magnetic field and the area are like this, so this is the area, this is the magnetic field, can you see that the n hat vector, what is the n hat vector? Do you remember what n hat is? N hat is the perpendicular drawn to the area, right? So if your n hat and the B field are along the same direction, so that means your theta is 0. So theta is the angle between n hat and the B field. So you have to remember that. So even in the electric field, electric flux, it was similar. Theta was the angle between n hat and the electric field. So here, theta is the angle between n hat and the B field. So here you can see theta is 0. If theta is 0, cosine theta is 1. Cosine 0 is 1. You can see your flux, magnetic flux, phi B, is maximum when the B field cuts the surface like this, when your N and B are in the same direction. It is minimum when will it be minimum? So assume that this is a surface. So this is like this surface, I am looking from this side, okay? And assume that your B field is also this way. So if this is your surface, this is a side view of your surface. N is like this, right? This is another example. Let's say example C. So in this scenario, your N hat and the B field are perpendicular to each other. In other words, theta is 90 degrees. And cosine 90 is 0. So this is the minimum flux that you can get. So when your surface, so this is your surface, right? When your surface is parallel to the B field, then there will be no magnetic field lines cutting the surface, right? For example, if this was your surface and field lines were going like this, it's just parallel, right? So the surface, so they don't cut the surface. So your magnetic flux will be 0. So this is the maximum flux you can have, and this is the minimum flux you can have, and this is a middle scenario where your B field and the n hat vector are with some angle which is not 90 or 0. Okay, so this is a recap of what we have done before. Instead of the electric field, we now have the magnetic field. Okay, so if you are okay with this equation, I want you to do this problem, and I want you to carefully look at the angle they have given. So try to figure out which angle they have given. whether they have given theta or something else. So figure out the correct theta and give me the answer. So the answer is B. So this is a very common mistake, especially in magnetic fields, because instead of the n hat direction, they usually talk about the surface. So if you read this question, they are saying find the magnetic flux through the loop when the plane of the loop and the magnetic field are at an angle of 30. So they are talking about the plane of the magnetic field. In other words, plane of the loop. In other words, they are talking about the surface, right? So if this is your surface and I'm drawing a side wheel, they are saying B field, this is the surface of the loop. They have given this angle, right? But we need the angle between n hat and the B field. We don't want the angle between the surface or the plane of the loop and the B field. We need the angle between the B field and the perpendicular to your plane of the loop. Okay, so what we really need is this angle. So this angle is what? Is 60 degrees, right? This is a 90. So if we apply, BA cosine 60, your B is 0.2. What is A? It is a circular loop. So pi r squared. R is 0.1 to the power 2 cosine 60. So when you do this, you will get 3.14 10 to the negative 3. And the unit should be, this is Tesla. This is meter squared, right? So Tesla meter squared. So your answer is B. Okay. So look carefully in magnetic field questions because most of the time they will talk about the plane of the loop. Okay. Most of the time they will talk about the plane of the loop. So are you okay with this? Yes? Okay. Now we are going to the lesson. We are going to look at the induced EMF. EMF means electromotive force. In other words, induced voltage. And we call this the Faraday's law. So let's see what is happening. So Faraday said, if your magnetic flux, so you know what magnetic flux is. Magnetic flux is given by BA cosine theta. So if your magnetic flux through a loop, through some object, changes with time. So if phi b changes with time, then it will create a voltage in your loop. Voltage means if there is a voltage, what will happen? Let's say there is some voltage here. What will happen? Current will start going through it, right? So Faraday gave us an equation to find this induced voltage or the EMF. What he is saying is, he's saying EMF, which is induced, is equal to the change in flux with time. Okay. So that is the equation. If you have n number of loops, so here we have one, right? If let's say you have n number of loops here, like a coil, if the number of loops are n, then the induced EMF will be n times this value. And can you see that there's a negative sign here? There's a negative sign here. So this negative sign is really related to the direction. So when they ask you to find the EMF, even if you find the value without this negative value, it is fine. Okay, because this will really tell you about the direction, which we will learn in few slides. So we will really learn how to find this direction using something called Lenz's law. Okay, so even if you get negative or positive values, you can just neglect this negative value for now. Okay, so it is just something to symbolize that the EMF that you get is opposing something. So we learn what it opposes. So are we okay with this equation? Okay. So the important thing is you will get an EMF only if your flux changes. So my first question to you is, assume that you have a B field. You have a B field, it's a constant B field, it's a constant one, and you have a loop inside this. So if nothing changes, if your B field is a constant and your loop is also just staying there as it is, will there be a EMF? Will there be an EMF? No. Is there a flux? Is there a magnetic flux in this one? Yes. So you have a B field and you have an area, right? So you have a flux, but you don't have an EMF. Why? Because the flux is not changing. So if this changed with time, then you will have an EMF. But right here, your flux is a constant, right? B times A. Even after 5 minutes, it will still be B times A. Flux doesn't change, no EMF. Okay. Now my next example is, let me erase this. Okay. Assume that you have the you have the loop. So this is the same place. Okay. Suddenly, what I do is I turn off my magnetic field. So here is the initial case. This is the final case. So initially I have the magnetic field and I suddenly turn off my magnetic field. Let's say this is t equals 0 and this is t equals, let's say at 1 second. Will I get a EMF? Will I have an EMF here? At the moment I turn off the magnetic field, will I have an EMF? Yes or no? So do we have an EMF or not? Yes or no? So I got one answer. Can I have more answers? Yes or no? So I got yes and I got no. I got both. What else? No, because there's no flux. Okay, what else? No, no. So my answer is yes, we have an EMF. Let's see why. So When do we get EMF? If there is a change in flux, right? Not because we don't get an EMF just because we have a flux. We get an EMF if there is a change in flux. So let's try to calculate this. So change in flux means flux final minus flux initial, right? That is your change in flux. And you divide it by the time. So what is your final flux? 0, right? No flux at the end because there is no B field. Do you have an initial flux? Yes, right? You have B times A. What is the time taken? I said 1 second. So do you have a flux here? Yes, right? Sorry, you have a change in flux. If there is a change in flux, there is an EMF. Okay, so do not just look at the flux. Look at the change in flux. So that is the keyword, change in flux. So if there is a change of flux, whether it is decreasing, increasing, vanishing, anything, if your flux changes, then there is an EMF. So are we clear with that now? So that is what this equation is. Okay. Now let's go to these 3 problems. I want you to read this carefully and tell me the answers. Is it C or A? Okay, let me draw something first before writing the equation. Let's say I have a big loop in this. I have the same magnetic field and I have a tiny loop in this. Nothing changes. Assume that nothing is changing, the magnetic field is not changing. What is the flux in this? Phi is equal to B A. So I'm writing a big A to show that the area is big here. In this, your phi will be B A, your area is small. Still, no matter, like, although the flux here is bigger, still there is no EMF, right? No EMF in this one and no EMF in this one because flux is not changing. We know EMF is only proportional to N and the change in flux. See, this is a change, not just flux, right? We didn't just have flux here. We have change in flux. So I got a question, is time inversely proportional? Not really. So in this equation, what you really have is the rate of change. Okay. So it's like it is proportional to the rate of change of flux. So always think like that. So this whole thing is like the rate of change of flux. It's like a slope, right? In a graph, the slope, something like that. So if your flux changes very rapidly, then you have more EMF. If your flux changes slowly, I mean like less rapidly, the amount it changes is less, then you have small EMF. So the answer should be C. It is proportional to the time variation of magnetic flux, not to the magnetic flux. Okay, so we can see using these examples why. No matter how big your flux is, if it doesn't change, no EMF. Okay, so it should change with time. So in this one. So what they're saying is initially the system has created some EMF and it is equal to this equation that we know. Delta phi B over delta T. So without changing any other parameter means whatever which caused this EMF, they haven't changed it. They have only doubled the number of loops. So they have doubled the number of loops in this. So what will happen when you double the number of loops? Your EMF also doubles, right? So your answer is B. When you double the loops, you double the EMF. So similar to the first one, second one, I'm going to write the equation for the initial EMF. Okay. So in this one, so I don't know what they are really changing, so I can't nicely write an equation. So this is the initial for the new. So they haven't changed N. Seems like they are changing the diameter. So what will change the diameter? It will change the area, right? Area of the loop. We know area is given by pi r squared. So when you double the diameter, radius will also double, right? Yes, when you double the diameter, radius doubles. So when radius doubles, what will happen to your area? There's a square term here, right? So area will become 4 times. So when you double the diameter, your radius will also be double. Since you have a square term here in the area, your area will be 4 times. So we know when we calculate delta phi, we have an area term also inside, right? So when area becomes 4 times, what should happen to your new EMF? It should also become 4 times, right? Now your area is 4 times. EMF is also 4 times. So the induced EMF is 8. Okay. So these problems can be a little confusing because you might think just like a normal EMF problem. But here what they're saying is initially they have some EMF and without changing any factor which caused the EMF, they are doubling the diameter. That is what they are talking about. Okay. So answer is A. So are we okay with these 3? Yeah. Okay. So there are 2 problems here. Try to do it and tell me the answers. I got 5, I think. Yeah. So the first one, the flux through a coil changes from this value to this value in 0.1 seconds. What EMF is induced in the coil? We know the equation. EMF is given by negative N delta phi. Delta phi is pi final minus initial, right? Divided by the time taken. So here, since we only have one coil, N will be 1. Even if you calculate without this negative sign, it doesn't matter. Okay, negative sign kind of tells you the direction. So final is 5, 10 to the negative 5. Initial is 4, 10 to the negative 5. And the time taken is 0.1. So when you do this, you should get 1, 10 to the negative 4. Since this is EMF is a voltage, volts. So I got negative 1 10 to the negative 4. This negative has no meaning, so you can just neglect it. So your answer is C. So all of you got the answer C. For the next one, a coil is wrapped with 200 turns of wire on a square frame with sides 18 centimeters. So N is 200, area is, it's a square, therefore 0.18 times 0.18 meter squared. So this is your area. For a square, you multiply length by height, right? Okay. A uniform magnetic field is applied perpendicular to the plane of the coil. So if this is your coil, the magnetic field is like this. Sorry, I just saw your chat. Yeah. So the answer Natalie gave is correct. Okay. So negative sign shows the direction. It kind of shows that EMF is produced due to something opposing a change. So we will learn about it in the next part. We will learn about that direction part in few slides. Okay. Okay. So here B field is like this and the plane is like this. That means your theta is 0, right? Theta is the angle between N hat and B. So your phi is, flux is directly B times A because the field and the N hat are along the same direction. Okay. If the field changes uniformly from 0.5 t to 0 in 0.8 seconds, find the average value of the induced EMF. So like we did before, EMF is given by negative N, final flux minus initial flux divided by the time taken. So let's find final flux and initial flux. So what is your final flux? It is B times A, but your B, final B is 0, right? So final flux is 0. Initial flux is B times A. And for that your B is 0.5 Tesla and A is 0.18 squared. So we can just plug the values now. N is 200, 0 minus 0.5 times 0.18 squared. Time is 8 seconds. So when you calculate this, you will get a negative sign. Positive sign. But we don't care about the sign here. And your answer is 0.41 watts, 405 watts, right? 405 watts. When you round it off, you get D. So if you want to know what this negative and the positive signs mean. So if you get a positive sign, okay, so we will learn it later. It means your EMF, okay, your EMF means something which will produce a current, right? It is a voltage. It will produce a current in such a way that currents B field. So we know when something carries current, it creates a B field, right? B field is same as the initial B field we had. For example, here we had a B field, let's say going this way. This way. So the EMF with the B field which will be created due to this induced EMF is also along the same direction. That is what this plus means. Here we got something negative, right? That means the B field that will be created due to this EMF. EMF means something which creates current, right? So the B field that will be created due to our induced EMF is opposite to our initial B field. So it will be opposite to this B field. That is what it means. It is the direction. So this negative sign represents it is opposite to your initial B field which caused the change. Here positive means your EMF or the B field which is created by your EMF is also along the same direction as your initial B field you had. So it is along this. So we will learn about it in Lenz's law more. Okay. Okay. So before going to the Lenz's law, there is one more thing we have to know. It is about the EMF induced in on a moving conductor. So this is the classic example we usually take to derive this expression. Derive this equation. So let's try to derive it. So here what do we have? I have this loop-like thing. Can you see what I'm drawing? So I'm drawing on top of a loop. So I have this loop-like thing. And on top of it, I have this conductor which can move. Okay. So if this conductor is moving this way, can you see that there is a change in flux? So initially your flux will be due to this area, right? Initial flux will be due to this area. And when this conductor moves to some position, let's say it comes here, then your area will be this big area, right? So are you okay with the change in area? So initially your area is this. And if your conductor comes here, now your loop is bigger. So it has this whole area now. So the change in flux is really due to this small area, right? So if we can find B hasn't changed, your B field is a constant. If you can find this small area, then you have the change in flux. Am I correct? So this A, I'll write delta A for now. Is equal to B delta A. So delta A is the change in area. So change in area is this, right? Okay. So now I'm going to erase the mess I created. And I'm going to ask you to tell me the area of this square, not a square, the rectangle. So assuming that the length of your conductor is L, we know one side of the square, right? We know one side is L. Now the problem is figuring out this length. This length. It is the distance the conductor traveled, right? Initially it was here and now it is here. It is the distance that your conductor traveled in some time. Let's say that time is delta t for now. How can you calculate a distance something traveled? Do you remember this equation? Velocity is equal to d over t. From this, we can get that the distance traveled by the conductor is velocity times the time taken. So in other words, your distance d is equal to v times delta t. It is the distance traveled by the conductor in delta t time. Okay. So what I'm going to do here is I'm only going to take this part of the equation and I'm going to plug what I got. So the change in flux is B times delta A. Delta A is this. L V delta T divided by delta T. So delta T get cancelled and I am left with BLV. So this is an equation that you have to know. So if you have a moving conductor in a magnetic field, okay, this is just a moving conductor in a magnetic field, then there will be a EMF induced in your conductor. And it is given by B times L times V. B is the magnetic field strength, L is the length of your conductor, V is the speed of your conductor. So in examples, it might not be easy for you to derive this over and over again. So that is why I'm telling you that you have to know this equation. This is like a part of the theory. So with the equation in mind, I want you to try this example. So the answer is C, right? So your answer is correct. So it is. So when you just read this question, let's say you didn't know this equation, then it's going to be very hard. Okay, so you have to know this. So if you have a moving conductor in a magnetic field, the induced EMF is given by this equation. And it doesn't even have to be a loop. Even if you have a conductor moving, then there will be an EMF. B is 6, 10 to the power negative 5. L is the length of your wing. And the velocity is the velocity of your plane, 20.225. So when you do this, you should get the answer 0.81 volts. Okay, so there are only two types of questions that they can give. One type of question is a loop is in a magnetic field, like the previous ones we did. Okay, loop in the magnetic field and the magnetic flux through the loop changes. So when that happens, you will be directly applying the main equation. And if you see conductors moving in magnetic fields, you will use this equation. Why? Because it is hard to figure out this one. It's the same thing. We know that the two equations are the same and this is an easy version. Okay, now let's go to the next part. Lenz's law, or the law which we use to find the direction of the induced EMF. So Faraday's law, the previous one which we did, so delta phi over delta t. So this law really tells us the magnitude of the EMF. But to figure out the direction, we are going to look at Lenz's law. This is easy to figure. This is a better law to figure out the direction than the negative or the positive sign we had at the beginning. Okay, so Lenz's law, the first thing that you have to know is the direction of the induced EMF or the reason why the EMF happened, or why it induced. Why did it induce? The reason why it happened is because your loop doesn't like change. Okay, loop or your conductor or anything does not like change. So if it doesn't like change, what will it do? It will resist it, right? It will oppose it. So that is the basis of your Lenz's law. So that you will figure out the direction by thinking along this. If there was a change, the EMF which will be induced will oppose or resist the change. It will try to make the system back to normal. Okay, so we are going to have that in mind when we are trying to figure out the direction. So your first step. First step is you are going to figure out what's happening to your magnetic flux. For example, let's assume that you have a loop here. So it is the same loop. So think that this is at the front facing you and this side is like at the back. Okay, so it is a vertical loop like this. And you are bringing a magnet towards this side. Okay, so this is my example 1. So what can you tell about the magnetic flux? Is it increasing or decreasing? So if you are going to bring a magnet closer and closer to this loop, what is happening to the magnetic flux in the loop? Can I have answers? Is it going to increase or decrease? Yes, I got one answer. Any more answers? What will happen to phi B? Phi B? Increase or decrease? Phi B means the magnetic flux through the loop. It's going to increase, right? Does it make sense? When you are going to bring a magnetic field closer, phi B increases. It increases which way? In this direction, right? Your magnetic flux increases in this direction. So are you okay with the first part? Figuring out what is happening to your magnetic flux. So this was what's happening to this, right? Your magnetic flux was increasing towards left side. So let's look at this example for now. So still we haven't really figured out the final answer. We are just going through the steps, okay? Okay, now can you tell me what is happening to this one? Is it increasing or decreasing? And which way? So here you have a magnet here and they are going to take the magnet away. Can you see? The velocity is this way. What is happening to the magnetic flux? Is it going to increase or decrease? It is going to decrease. Phi B is decreasing. Which way? So the magnetic flux in this direction, which was in this direction, decreased, right? Initially you had magnetic flux this way, and because we are going to take this magnet away, magnetic field which was along this direction is decreasing now. Okay, so we have now figured out what was happening to the magnetic flux. Now the second step. Second step is figuring out what you can do to resist it or to put it back to normal. So let's take the example 1 again. if the magnetic flux is increasing this way, what should you do? You should what should you do? Let's say you have the ability to create a magnetic field. Okay, let's say you can create a magnetic field to oppose this. So to oppose this, what are you going to do? You are going to create a magnetic field this way, right? Yes. Do you get it? See, you are going to figure out the induced magnetic field, and induced magnetic field should oppose the change in flux. So initially what happened was, when you begin this closer, magnetic flux this way increased. So to oppose it, what are you to oppose it, what's going to happen is a magnetic field should be created this way, which I'm going to write B induced, to oppose it. That's the only way it can be opposed, right? If the magnetic flux this way increases, there should be a magnetic flux in the other way to cancel it off. So are you okay with this one? Yes? No, yes, yes, okay. Okay, so once you have figured up to here, B induced, then it's easy. Then what are you going to do is, you are going to take your right hand and figure out what kind of current will create this induced magnetic field. So can you put your right hand rule and tell me which way should the current flow to create this? So keep your thumb in this direction and your fingers will bend this way, right? So these are your nails. So my hand will be flipped, okay? So this is the induced magnetic field. You figured out the direction of the induced magnetic field. Then you are going to figure out what sort of a current can create this magnetic field. So this is how my fingers were bent. So an EMF or a current in this direction, so in this one, counterclockwise. Yes, it's counterclockwise, right? So counterclockwise current or an EMF will create this B field. So the direction of induced EMF is this. So here it is counterclockwise, CC. Okay. So if you can figure out the induced B field, then it is easy. Then it is just right hand rule. So are you okay with that? With the first example? Yeah, the simpler right hand rule. Yes, the simple one, where you can do anything you like, interchange between current and the magnetic field, that one. So now let's look at the second example. So here what is happening? The magnetic field this way is reducing, right? That is what is happening. That's step one. Magnetic field this way is reducing, but it doesn't like change. It doesn't like reduction. So it should create a magnetic field in the same direction to stop it, right? So the induced magnetic field is also this way. So do you get this? Do you understand it? Why it is this way? Because the magnetic field towards your left is reducing. So it doesn't like reduction or any change. It is going to create a magnetic field to stop it from changing. So this is your magnetic field induced. So now you are going to put your right hand rule to figure out the direction. So use your thumb. So your fingers will point like this. Like it will curl the other way. Yes. So current will go like this. So current will go clockwise direction in this. So this way. So this is like the back behind. This side is the behind of the loop. So are you okay with this, figuring out this? So these are the 3 steps. Figure out what is happening to the magnetic flux. Then figure out what kind of a magnetic field can resist it or stop it from happening. And that will be your induced magnetic field. And once you know that, you are going to put right hand rule to figure out the direction. Okay? Okay. So tell me the answer for the first one first. So the answer is D. Okay, D. According to Lenz's law, induced current is created because it will oppose the effect which produces it, right? It's going to oppose it. Okay. Now I want you to try these 2 problems. So I will draw it. So let's say you have this loop. So this is the first one. There is a magnetic field this way initially, and suddenly this magnetic field vanishes. So that is the problem. Which way will be your EMF or the current? In this one, what's happening? So still you have the magnetic field this way, but your magnetic field grows stronger and stronger this way. So you all are going to tell me what is going to happen to your induced current. Which way will be your induced current? So in this one, what is happening? In the second one, in this one, first one, the magnetic field vanished, right? So this suddenly vanished. So the loop doesn't like it, right? So it is going to induce a B field in this direction to stop the change from happening. Okay, so we know the induced, so this is the induced B field. So to create that B field, your current should be going this way, right? So for the first one, it is counterclockwise direction. For the second one, your B field keeps growing stronger and stronger in this direction. So it doesn't like change. It is going to create a B field to cancel that effect. It's going to stop it from growing. So this is the induced magnetic field. So what sort of a current will create that magnetic field? So this is the current that I got. So it is clockwise. So do you get these answers? So try it few times. Okay.